4 of live TA discussion. Uh, so today I'm going to discuss about the stability and eigenvalue eigenvectors of a systems of a matrix and the stability of a system, and also discuss about the Lyapunov stability, how to calculate, how to find out the Lyapunov stability of a system. So before start the discussion, I would like to just ask if any questions regarding today's discussion, if you have already studied or in the previous discussion, do you have any kind of queries so that I can start with those things? So it seems that okay. So Miss Vishalakshi, am I pronouncing your name correct? Do you have any queries regarding today's discussion or the previous discussion or anything?
Hello, good afternoon, sir. Actually, I missed
Good
the
afternoon.
last two, three discussions.
Okay, okay. So, okay. So you can go to that recorded
Link.
video and check that.
Uh,
So, okay. So I will start. Then I'll start with the today's discussion. That is the eigenvalue, eigenvectors, and the stability of the system. So let me share my screen first. So it's visible, right?
yeah, it is visible.
Yeah. So first I'm going to talk about the eigenvalues and eigenvectors. So can you tell me what is the eigenvalue? I mean, definitely, I assume that you know what is eigenvalues and eigenvectors. So can you tell me what is the actual definition of eigenvalues and eigenvector? Okay. So first of all, to tell about the eigenvalues, first I'd like to discuss about the eigenvectors. So eigenvectors, basically, we know that if let's say A is a square matrix, okay, and V is a vector. So we know that when we multiply a vector with a matrix, what it happens? Probably its direction changes. So when we multiply a vector with a matrix, there is a probability that its direction changes, which is normally happen. But the eigenvectors are the special type of vectors. So when we multiply, so basically eigenvectors are the special types of vector. Okay, so it says that when we multiply A with a V, its direction never changes. Either it contracts, but either it contract or it shrunk or stretch or opposite direction is opposite or in the same direction. So this value, this scalar multiplication basically defines whether the vector is will shrunk or stretch or opposite or in the same direction. So this scalar value is said the eigenvalue, and the vector V is called the eigenvector of matrix A. So up to that point, we know that eigenvalues and eigenvector contains the characteristics of the system or of the matrix basically. So when we say that, if we say like, do you know the word Hurwitz matrix? Do you know? You just keep on interacting. Like, do you know the word Hurwitz matrix? Have you ever heard that word Hurwitz matrix? So, Hurwitz matrix basically it says that the eigenvalues of matrix always lie in the left half of complex plane. So when a matrix, let's say A is a matrix, if it's all the eigenvalues lies in the left half of the complex plane, so we say that those matrix, we say that A matrix is a Hurwitz matrix, or we can say it's a stable matrix. So basically, we know the stability of a matrix using the eigenvalue. Now, first of all, I would like to start with an example, like how we calculate the eigenvalues and the eigenvectors of a matrix. And then we will check whether for a single, uh, first I will start with an example that a system has a distinct eigenvalue. So we know that distinct eigenvalues always gives a distinct eigenvector. But sometimes it's possible that a matrix has only a matrix has the repeated eigenvalues. Let's say if it is the matrix is 3 cross 3 matrix, it's possible that all three eigenvalues are the repeated one, or then two of them is a repeated one, and one is a distinct one. So for that case, do we get distinct eigenvectors or not? If we do not get a distinct eigenvector, what should we do? So this why we need this why we basically care about the distinct eigenvector. You will you will basically get to know in the later classes, because in the next class we will get to learn the how to diagonalize the matrix and all those things. So first in these classes we will get to know first how to find out the eigenvalues and eigenvectors. So let's start with an example. So the example is, so let's say I have a matrix which has 0 0 1 1 0 minus 11 and 0 1 minus 6. So to find out the eigenvalues, what should we do? We have to find out the determinant of this lambda I minus a. We just equate it equals to 0, and then we get the values of lambda. Either you do lambda I minus a, or you can do determinant of a minus lambda I. Both are same. I mean, you will get definitely same result using any of them. So at any point, if you do not understand or if you find difficult to understand, please stop me. Okay. So lambda I minus a, if we do lambda I minus a, what I will get? Lambda 0 6 minus 1 lambda 11 and 0 minus 1 lambda plus 6. Equating this to 0, what I will get? It's a lambda into lambda 11 minus 1 lambda plus 6, and 0 I'm not writing it because after all multiplying with 0 you will get a 0, and then 6, what I will get? Lambda 0 minus 1 So this is lambda into lambda square plus 6 lambda plus 11, and here 6 lambda equals to 0. So you will get lambda cube plus 6 lambda square plus 11 lambda plus 6 lambda. You will get 17 lambda. Okay. Uh, just a minute. Plus 11, 6 into lambda lambda into lambda square plus 6 lambda plus 17. You will get 0. 0, 0 minus 6, 1, 0 minus 11, 0, 1 minus 6. Think I have done some mistake. Let me check. Oh, so the result is lambda equals to. So if we do the equation 5, 1, 6, 17. So what are the lambdas? Lambda equals to 0, lambda equals to minus 3, lambda 1, lambda 2, plus 2 root 2 I, and another is definitely complex number, minus 3 minus 2 root 2 I. So what do we get? We get a 3 different eigenvalues, and uh, then we have to do the A into V. So A minus lambda I into V equals to 0. So you have to put the all the values of lambda one by one. First, you have to put the values of lambda 1 over here and then calculate the values of V. In that way, you will get the answer, the eigenvector. Okay. So let me start with a different example. I mean, in this example, you will get you got basically a different answer. Let me do this. Let's start with another example where we get, let's say, A equals to 2 minus 1 0, minus 1 2 minus 1 0 minus 1 2. Okay. Yeah. So this is basically, you can see this is basically a symmetric matrix, and you will get to know that for any symmetric matrix, if the system is a positive definite, if this matrix is a positive definite, then you will get a symmetric positive. For symmetric positive definite matrix, you will get a real eigenvalue. So let's check. First, you have to do determinant of lambda I minus A equals to 0. So what you will get? Lambda minus 2, 1, 0. Oh, 1, lambda minus 2, 1, and 0, 1, lambda minus 2. This is equal to 0. So what you get? Lambda minus 2 into lambda minus 2, 1, 1, lambda minus 2, minus 1, 1, 1, 0, lambda minus 2 is equal to 0. Yeah. So what do you get? Lambda minus 2, lambda minus 2 whole square minus 1 minus lambda minus 2. So what do you get? Lambda minus 2, lambda square minus 4 lambda plus 4 minus 1, 2. Excuse me. So this is lambda minus 2, 4 lambda plus 3 minus lambda minus 2 equals to 0. We will get lambda cube minus 8 lambda square plus 3 lambda minus 2 lambda square plus 8 lambda minus 6 minus lambda minus 2 equals to 0. So lambda cube minus 10 lambda square plus 11, 11 minus 1, 10 lambda minus 8 equals to 0. So what do we get? 1 minus 10 plus 10 minus 8. So lambda equals to 8.986, lambda 1, lambda 2, some problem is happening over here. Sorry, this is plus.
It is minus lambda plus 2.
Yeah, this is plus. Yeah, thank you. And this should be minus 4. So it is 1 thing, and this is minus 4. So it should be 9, 3. It should not be, something is wrong with that. Could you please check, I mean, whether there is some problem with these calculations or not, because something is problematic with here.
Let me check, sir. What is your answer? Final answer?
It's basically coming out as a some imaginary number,
Real
which
values,
should
right?
not,
Real
it should,
real values, right?
yeah, all the values should be real, but it's
Okay.
comes out
Okay.
as a,
Tell me the final characteristic equation.
it's I mean, first check that determinant of lambda is basically doing it correct, right? Lambda minus 2, 1, 0, then 1 lambda minus 2, 0, and 0, 1 lambda minus 2. This is correct, right?
Yeah, that's correct.
That's correct.
In the,
So
in the multiplication, I think something wrong.
yeah, so that's the
Lambda
thing.
minus 2.
So just lambda cube, lambda square. Okay, sorry, I have done here mistake. It should be 4 lambda square. Yeah, it should be 4 lambda square. Okay, now this should be 6 lambda square. Yes, I hope everything is okay. And 6. Yeah, so please coming out. So one is 2, another is 2 minus root 2, and lambda 3 is 2 plus root 2. So you see that this is the symmetric positive definite matrix. For a symmetric positive definite matrix, I will explain later the how can you find out the positive definiteness of a matrix. and you will get a real eigenvalue. And all the eigenvalues are distinctive. So distinctive means all the eigenvalues are different. So for each eigenvalues, the corresponding eigenvector is always be a different one. So for lambda 1, you will get a eigenvector v1. For lambda 2, you will get eigenvector v2. For lambda 3, you will get eigenvector v3. But this is not the case for every matrices. So sometimes you can see there are some matrices for which you will get a repeated eigenvalues, and because of the repeated eigenvalues, you may or may not get a different eigenvector. So I will just discuss about, I'm going to discuss about those matrices first. So this example shows that your matrix have a a repeated eigenvalue, but you will get a different eigenvector as well. So before that, so this is your matrix. So I'm going to here discuss about the two things, geometric multiplicity and algebraic multiplicity of eigenvalues. So just ask me one question. So do you have any idea what is geometric multiplicity or algebraic multiplicity? You have no idea, right?
No, 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 no.
Okay. So let's say algebraic multiplicity. First is, and just create a node box. So algebraic multiplicity. So we will these are basically required for diagonalization of a matrix. So which we will learn in the next class. So algebraic multiplicity basically, if any matrices have a different repeated eigenvalues, so how many repetition of that eigenvalues is there? So basically, number of repetition of eigenvalue of a matrix. Okay, so if let's say A is a 3 cross 3 matrix. Okay, and its eigenvalues are lambda 1, lambda 1, and lambda 3. So that means here two
Then,
eigenvalues.
sir, then algebraic multiplicity is 3. Is it like that?
No, so algebraic multiplicity of lambda 1. So the algebraic multiplicity of lambda 1, let me,
Lambda 1 is
algebraic,
2.
Algebraic multiplicity of lambda 1 is 2 and algebraic multiplicity of lambda 3 is 1. Right, because lambda 3 is appears only once time, but lambda 1 appears 2 times.
Yeah,
Okay.
yeah, I get it.
So this is algebraic multiplicity. Now, what is geometric multiplicity? So geometric multiplicity says there's sometime we can we will see that for lambda 1, the corresponding eigenvector. So for lambda 1, if there exists corresponding eigenvector, let's say 2, if there two eigenvector exist, because lambda 1 is only lambda 1, though lambda 1 appears twice, but lambda 1 actually a single number. But for this lambda 1, if we get two different eigenvector, so if we apply a minus lambda 1 I into v equals to 0, and then we solve these equations, and we say if we get v 2 v, let's say one v1, another is v2, then we say the geometric multiplicity of lambda 1 is 2 as well. Is it clear to you? Am I clear to
Can you
you? Huh.
can you repeat? Can you repeat, sir, once
Okay,
again?
so I'm saying, so how do we calculate the eigenvector? So first of all, we calculate the eigenvector using this equation, right? Using
Yeah,
this
that's
equation, we
okay.
calculate the eigenvector. So lambda 1 is appears twice, but obviously if we put the lambda 1 over here, this equation both time is same. This a minus lambda 1 I, this equation is same for both cases, because lambda 1 I'm just putting lambda 1 over here. There is nothing, any other lambda 1 is over there. But for single lambda 1, we know for this, for any eigenvalue, we know that always exists a eigenvector. But when the repeated eigenvalues exist in a system, for that case, can we get a 2 eigenvector? Or if the repetition is 3, can we get a 3 eigenvector for the same eigenvalues? Is it possible or not? So sometimes it is possible that for a repeated, if the eigenvalues, if the repetition of our eigenvalue is 3, sometimes it is possible that we get a 3 different eigenvectors. But sometimes it's possible that we will not get a 3 different eigenvector. We will get only one eigenvector for a repetition case. That means for lambda 1, only one eigenvector exists. If it's possible, if it happens, if let's say the repetition of lambda 1 is n times, and there exists only one eigenvector corresponding to lambda 1, then the geometric multiplicity of lambda 1 is 1. If there exist n eigenvectors corresponding to lambda 1, then the geometric multiplicity of eigenvector, sorry, of lambda 1 is 10. It happens only for repetition case, not all cases, because we know if distinct eigenvalues existed. Let's say for 3 cross 3 matrix, there exists lambda 1, lambda 2, and lambda 3. So we know we will get a one corresponding eigenvector for lambda 1, another corresponding eigenvector for lambda 2, and another corresponding eigenvector for lambda 3. But if for, let's say, 3 cross 3 matrix cases, if the eigenvalues are lambda 1, and lambda 3, so there is a 2 repetition of lambda 1. So for that case, do we get 2 different eigenvalues for lambda 1? Because we know there exists an eigenvector corresponding to lambda 3. So that is a different case. I mean, that is, you do not worry about that. But since there is a repetition of eigenvalues, if repetition of lambda 1 is twice, so do we get 2 different eigenvector for lambda 1 or not? If we get a 2 different eigenvector for lambda 1, for this case, so we will say the geometric multiplicity of lambda 1 is 2. Is it clear?
Yes.
So I'm just explain you with an example. You will see the first example I'm going to show you, that you will get you will get different eigenvectors for repeated eigenvalues, and then I will show that you will never get a different eigenvectors for repeated eigenvalues. So what we'll do then? So this is the first matrix Okay. So the eigenvalues, I'm not just going to A minus lambda minus AI, sorry, lambda I minus A equals to 0. And I'm not calculating this whole thing. I'm just writing down lambda 1, you will get minus 2, lambda 2, you will get minus 1, and lambda 3, you will get minus 1. Okay. So here you can see, that lambda 2 is repeated one. So first I will find out I'm going to find out the eigenvector for lambda 1. So here I apply A minus lambda 1 I. This is my A 0 to 0 minus 1 minus 3 0 0 0 minus 1 minus lambda 1 is minus 2 minus 2 minus 2. And this is, let's say, V11, V12, V21, and V3. This is basically the eigenvector that I'm going to find out. And this is 0 0. So this is 2, this is minus 1 0, this is 2, this is again minus 1 0, and this is 0 0 and 1.
It is 3, right, sir?
Yes.
1 plus 2.
Did I again something? Did I do again wrong? This is minus 2 minus 1 0, right? And then this is 2, and then minus 3 plus 2 is minus 1, again 0. And this is 0 0 minus 1 plus 2 is 1, right? I think I have done correct. Okay. So there are 3 equations, 3 unknowns. You have to solve this. Okay. So you can do this either row elimination method. Using row elimination method, you can do, or you can just simply write down the equation form and just calculate. So I'm doing using the row elimination method. So if I do the row elimination method, what do I get? Let's say what row elimination I'm doing. I'm just writing down over there. Just for this matrix, I'm just changing the second row. The second row is basically, so what we'll get is 2 minus 1 0 0 0 0 0 0 1. Now if I do these things, so what we get? So V31 has to be 0, right? V31 has to be 0 to satisfy this equation. So V31 is 0. Now what is V21 and V11? So V11 is, if I'm taking V11 as a 1, so V2 I have to take as 2. Then it is, this vector comes out as a solution, right? Up to this point is okay to you? Is it okay to you? Yeah. Miss Lakshi, is it okay to you that how this eigenvector comes out?
Okay.
right? So, or you can also do this kind of thing. You can write 2v11 minus v21 equals to 0 and v31 equals to 0. So from here you get the v31 is equals to 0. So v11, what is v11? v1, if I take v11 as 1, then obviously v21 has to be 2. Then this equation should be 0, right? So, or you can, this v11 and v21, these two are free variables. You can choose anything. Either you choose v11, v21 as 1. If you choose v21 1, then what should be the v11? v11 should be a half. If v11 is half, or this could be half 1 0. This is also an eigenvector for this case. Okay. But these two are not independent one. Basically, if we see in a, let's say, xy plane, because the z axis is 0, so this is basically x is 1 and y is 2. So this is, let's say, this is the one vector, this is 1 2 0, let's say. And if we say x is half and y is 1 1, so let's say this vector is half 1 0. So these two are not linearly independent, right? In the same line, these two vectors are exist. So either you choose this one or this one, it doesn't matter. They are not a defined eigenvector. So distinct eigenvector, I'm saying that both, all the eigenvectors has to be linearly independent. So what is linearly independence? Linearly independence means, let's say I have v1, v2 up to vn. There are n number of vectors are there. Okay. So if I say the alpha 1 v1 plus alpha 2 v2 plus dot dot dot, let's say alpha n vn equals to 0. If there are any combination exist, let's say alpha 1 alpha 2, any non-negative values of alpha 1 alpha 2 is exist, and this solution satisfied, then we say the v1 v2 up to vn are not linearly independent. If and only if these v1 v2 vn are linearly independent, if alpha 1 equals to alpha 2 equals to alpha 3 equals to dot 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 alpha n, all the eigenvalues, if we put all the scalar term equals to 0, then we get this solution exists. Then we say our vectors v1 v2 up to vn are linearly independent. If there exists any term, let's say up to, let's say alpha 1 alpha 2, let's say alpha 1 alpha 2 up to alpha n minus 2 are 0, but alpha n minus 1 is, let's say, minus 1 and alpha n equals to plus 1. If this kind of condition apply, arise, and this solution satisfied, then we cannot say that all the eigenvectors are linearly independent. Okay. So this is the linearly independent. This is a check of linearly independent. So here you can see that this vector and this vector, these two vectors are not linearly independent. They are just scaled down. This vector is basically the scale down of this vector. So they are in the same direction. So for eigenvalues lambda 1 equals to minus 2, I get this eigenvector. Now I have to check for eigenvalues lambda 2 equals to minus 1. Do I get different eigenvector or same eigenvector? So what is a minus lambda 2I into v2 equals to 0? So 0 2 0 minus 1 minus 3 0 0 0 1 minus, this is minus 1 minus 1 minus into v21 point out as the 1 2 1, 3. So this is V22 and V32. This is equal to 0, 0, 0. So what do I get? It's 1 minus 1, 0, 2 minus 2, 0, and 0, 0, minus 1. So 0, 0, 0. No, no. This is minus 1. Yeah, 0, 0, 0. V21, V22, V32, 0, 0, 0. So first eigenvector, what can I choose? I can choose V21 as 1, right? V22 as 1 and V32 as 0. So V21 minus V22 equals to 0. This is 2V21 minus 2V22 equals to 0. Okay. And V33, we can choose anything, right? Right, because here, if we multiply 0 with any values, we will definitely get 0. So we can choose 0, V33, anything, V33, V32, anything. We can choose sorry, this won't be a
Sir,
V.
it is V23, right?
V23, we can choose V23, anything, right? Because we can multiply, if we multiply anything with 0, we will get 0. So this is one eigenvector. What another eigenvector I can choose? Let's say another eigenvector I'm pointing out as a V2 prime. I can, one thing remember, eigenvector cannot be 0. I mean 0, 0, 0 cannot be an eigenvector for any system. Okay, because 0 is very trivial. If we multiply a matrix with a 0 vector, you will definitely get a 0. So it's a very trivial. So we cannot choose 0, 0, 0 as an eigenvector for any system. So let's say what extra, what another thing I can choose. If I choose V2 V21 as 0, V22 as 0, and let's say V23 as 1. This is also another eigenvector, and these two are linearly independent, right? Because if we multiply alpha 1 with 1, 1, 0, and alpha and add with alpha 2, 0, 0, 1, for what value of alpha 1, alpha 2, you will get this 0, 0, 0. You will see that only alpha 1 equals to 0 and alpha 2 equals to 0. Only this alpha 1, alpha 2 value, for this alpha 1, alpha 2 value, you will get this 0, 0, 0 solution. So that means these two are also linearly independent. So what we see, the for lambda 2 equals to minus 1, we get two distinct eigen vectors, which are v2 or 1, 1, 0 and 1, sorry, 0, 0, 1. Okay. So you see that it's not necessary, if you get a, if a system have a repeated eigenvalues, you may get different eigenvectors for that repeated eigenvalue, corresponding to that repeated eigenvalue. But there are also, let me explain with another example, the same concept. So here the matrix is 5, minus 1, 0, -1 5 0 1 -1 4. So if we do determinant of a minus lambda I equals to 0, what do we get? We get so lambda minus 5, sorry, 5 minus lambda 1 0 -1 0 -1 5 minus lambda 0 1 -1 4 minus lambda, right? So if you solve these equations, you will get, I'm not writing down the whole thing. So you will get lambda equals to 4, 6 and 4. So that means there are two repeated eigenvalues. So I'm just sorting it down. Lambda 1 equals to 4, lambda 1 equals to 4 and lambda 3 equals to 6. So what are the eigenvalues for that case? So I'm just replacing lambda 1 in this equation. I'm just replacing lambda 1 in this equation. What I get is a minus lambda 1. It's 1 -1 0 -1 1 0 and 1 -1 0. Right? What are the, it's a v11, v12, v13 and this is 0 0 0. Okay. So what v do I get? The v1 that I will get is, I can choose v13 anything. Let's say I choose v131 and for that case 1 1. This is another eigenvector, right? If I choose this v11, v11, v13 in this format, I will get definitely 0 0 0. I can choose v1 prime as 0 0 1. This is also another eigenvector. Okay, that means we get two eigenvectors, two distinct eigenvectors for repeated eigenvalue lambda 1 equals to 4. Okay, and now, and why basically we need to find out these two distinct, why we are basically care about this distinct eigenvector. It, you will get to know in the next class, where we will find out how to diagonalize the matrix. We'll get to know the how to diagonalize the matrix. So for that case, it is requirement, the distinct eigenvector is required basically. And if we see the last 6 case, -1 -1 0, and then it would be -1 -1 0 and then 0 0. Oh, sorry, not 0 0, it is 1 -1 and -2. So let's say v31, v32 and v33, 0 0 0. So here, either you write down this in equation format and then solve it, or you do the Gauss elimination method. So I prefer the Gauss elimination method. You can do any of this approach. So what do I get? Sorry, this will be plus, no, minus 0 0 0, and I change R3 prime as well. R3 minus R3 plus R1. So if we do, this is 0, this is -2, and this is -2. So what should I choose? Now V3 equals to, if I choose V331, so V32 should be -1 and this is 1. Right? So for lambda 1, So basically, for lambda 1, corresponding eigenvectors are, what are those eigenvectors? Triple 1, 0, 0, 1, 1, 1, 1, and 0, 0, 1. And for lambda 2, corresponding eigenvector is 1, -1, 1. So we get three distinct eigenvectors for eigenvalue. So up to this point, it is okay to you, right? Any kind of difficulties to understand? I assume there is no difficulty to understand, right?
No.
Okay. So now come to the next point, what I have said previously, that for a repeated eigenvalue case, we may not get always a different eigenvectors. Okay. So in that case, what should we do? We use a term, we use the concept of generalized eigenvector. So how these generalized eigenvectors, how to find out this generalized eigenvector? I just explained it with the
Let me
example.
ask one question, sir.
Yeah, yes, yes,
Let me ask one question.
yes,
So, characteristic equation is determinant of lambda I minus a equal to 0, right? So
yes,
that
lambda.
in that matrix, instead of lambda I minus a, we can take a minus instead of a minus lambda I minus a is also okay, no?
Huh, obviously, I mean, you can choose either this or
Okay.
this. Both, using both, you will get the same answer, because ultimately, this is what is this? If we take a minus common from this matrix, you will get minus determinant of lambda I minus a equals to 0, right? So ultimately, obviously, this term should be equals to 0, then you will get the answer, right? So there is, either you choose a minus lambda I or lambda I minus a, you will get the same answer. Okay.
Okay.
So the generalized eigenvector concept, I'm just explaining this using example. So let's say here I'm using a matrix. It's the upper triangular matrix. The good thing about upper triangular matrix is this. This is upper triangle because you see that the elements, the diagonal elements, and above the diagonal elements, all are the non-zero term, whereas the lower term is the zero term. So this is called upper triangular matrix. When the opposite case happens, if the lower triangular one, all the non-zeros, and upper triangular one, the zeros, then we will say the lower triangular matrix. So what is the good thing about this upper triangular or lower triangular matrix is that if you see this kind of matrix and someone says that what are the eigenvalues of this matrix, you do not need to calculate determinant of a minus lambda. You can say the eigenvalues by seeing the matrix, all the diagonal elements for the diagonal matrix, upper triangular matrix, and lower triangular matrix, the eigenvalues always lies in the diagonal term. Okay, so here the eigenvalues are 2, 2, and 1. So you can check, you can check whether the determinant of lambda I minus a is equals to 0 or not. Is equals to 0, you will get this lambda to this lambdas or not. But By seeing this matrix, you can easily tell that what are the eigenvalues of this matrix. Okay. So now I'm going to show you that here for the repeated eigenvalue case, I will not get I will not get different eigenvectors. So it is 2, 1, -2, 0, 2, -1, 0, 0, 1, minus 2, 0, 0, 0, 2, 0, 0, 0, 2. Let's say this is V11, V12, and V13, and this is 0, 0, 0. So what we get 0, 1, -2, 0, 0, -1, and 0, 0, -1. So here in this case, what are the equation you get? V11 minus 2 V12 equals to 0. Okay. The another thing is minus V13 equals to 0. So for sure, you know that the V13 should be 0. And what are the V11 and V12? So if we choose V11 as 1, so V12 as 1, so V11 should be 2. Right? If we choose V11 as 1, V12 should be half, whatever. So you can do anything, you will not find a different eigenvector for this case, because all the eigenvector you choose, this is let's say 2, this is let's say 1, this is the point. So it will always lie in this line. It will always lie in this line. You will never get a different eigenvector like this. It will never get. You will never get this one. You can check. So that means in this case, what is the geometric multiplicity of 2? Lambda 1 equals to 2. What is the geometric multiplicity? The geometric multiplicity is 1, right? Because whatever I do, I will not get any different eigenvector which are linearly independent with each other. But the algebraic multiplicity is 2, but the geometric multiplicity is 1. So in that case, we use the generalized eigenvector term. So okay, so I get the first eigenvector. Then how will I get the next eigenvector? So I do the different thing. A minus lambda 1 I. Let's say my next eigenvector is, let's say, U1 is equals to V1. I do this thing. So normally what we do? Normally we do the A minus lambda 1 I into V1 equals to 0. But in that case, we are not getting the different eigenvectors for repeated eigenvalues. We are not getting the distinct eigenvector for repeated eigenvalues. We are getting always, whatever we do, always we get the same eigenvector. So to solve this problem, we use this equation. A minus lambda 1 I into U1 is equal to V1. Okay. So what we get? 0, 1, -2, 0, 0, -1, and 0, 0, -1. This is U11, let's say U12 and U13, and this is V1. What did I get? This. So what are the equations that you get? U11 minus 2U12 equals to 2. Okay. And then uh, just a minute. Okay. Yeah. And here U12 equals to 1 and U13 equals to 1 and U13 equals to 0. Just a minute. Yes, I need to check something. Okay. So here, what I think I have done something wrong. Just a minute. Okay. So I do here I get the U11 equals to 0, U12 equals to -1, and U13 U13 is 0. Okay. So mistakes that happens over here. This is 0. 1 1 I think something is wrong. Let me check this. Something is wrong because these two equation doesn't imply anything.
Whether it is A minus lambda 1I into U1 equal to V1 or lambda.
Yeah, what did you say? Where is equals to? Hello? Hello?
So you're trying to find the second eigenvector, no?
Yeah, I just trying to find out the second eigenvector. That is
Corresponding to eigenvalue 2.
yeah, corresponding to eigenvalues 2. Exactly, because we need to find out the generalized eigenvector. Okay, so I need to find out the second eigenvector definitely. Just a minute. Okay, sorry. I did again a mistake over here. A big mistake.
It is not U11. It is
Yeah, yeah, yeah.
minus
Sorry. Yeah,
U12 minus 2 U13,
yeah,
which
yeah,
is
yeah.
equal to 2.
I wrote down this equation completely wrong. That is my fault. This should be V12 minus 2V13. That is should be equals to 0. And then I think this is the thing. Yeah. And here V13 equals to 0 minus V13 equals to 0. So this is basically the thing. So what obviously since V13 equals to 0, put V13 equals to 0 over here. So obviously from this equation you will get a V12 equals to 0 and you choose V11 anything other than 0 because 000 can't be an eigenvector. So you choose V11 anything. Let's say I'm choosing V11 equals to 1 because anyway V11 is multiplied with 0 and you will definitely get a 0 value. So this is one eigenvector. Okay. And so this should be the equation. That is the thing. Okay. So now here I did a great mistake over here. Again, you will get U12 minus 2U13 equals to 1. U13 equals to 0. So what you will get U11, you will get, let's say V11 I am choosing as 1, U13 is 0. So what should be the U12? U12 should be the 1. You can choose U11 here as 0 as well. So we get a two different eigenvector. It's clear, right? Sorry, I mean I did a great mistake over here. So so this is basically, so you see that from this equation, if we see that you will never get a different eigenvector because V12 and V13, these two always 0. These two term always 0, right? And whatever the value choose over here, you will always see, let's say instead of 1, let's say I want to choose 2 over here, which is basically the multiplication of the previous eigenvector. If you choose 0.5, that is also okay, but this is also lie in the same line. So whether you choose 1, 2, 3, 4, minus 1, minus 2, whatever the real number you choose, you'll always get a linearly dependent eigenvectors. Two eigenvectors are never be linearly independent. But here in this case, you get a linearly independent eigenvector. So let's say instead of, you know that u13 always be 0. And if u13 0, then to satisfy this equation, u12 has to be 1. And instead of u11 choosing as 1, you choose u11 as a 0. You can choose that because this is not a zero vector as well. So you see that this vector and this vector, these two vectors v1 and u1, these two are the distinct eigenvectors. So here we have to find out the eigenvector. So let's say the matrix, and I hope it is not difficult for you to find out the, okay. So v2 you will find out v2 over here. So I'm not finding out the v2 right now. So this is a similar type of solution. So if let's say your matrix is 4 cross 4, or let's say your matrix is 3 cross 3. Let's say A belongs to 3 cross 3 matrix. So here R is basically, I'm considering that R is a real number. So all the elements in a matrix are the real numbers. There is no complex number over here. So R is 3 cross 3 matrix, and let's say the eigenvalues are lambda 1, lambda 1, and lambda 1. So, and since repeated eigenvalues, and let's say, so here algebraic multiplicity is 3, and let's say the geometric multiplicity of lambda 1 is 1. So obviously, you using that equation a minus lambda 1 I into v, you will get v1. So solving equation, we get V1. Okay. Now, how to get the generalized eigenvector? You know that A minus lambda 1 I U1 equals to V1. This one is a generalized eigenvector. Okay. Now I have to find out the another generalized eigenvector. So I'm not going to stop over here. So in that case, you have to find out A minus lambda 1 I, let's say U2 equals to U1. This is another generalized eigenvector. Okay. Is it okay to understand? Is it okay to understand? I mean, is it okay for you?
Can you repeat second line? A minus lambda 1 I into U2 equal to
U1, the first eigenvector,
generalized
generalized
eigenvector,
eigenvector.
right?
Okay.
Okay.
Okay. So you can do these things, or you can do, let's say, I'm just writing it with a different. So what if we multiply both sides by lambda 1 I? So what we get? Lambda 1 a, so lambda 1 I multiplying both sides with the a minus lambda 1 I. So we will get a minus lambda 1 I square into u1 is equal to a minus lambda 1 I into v1. So a minus lambda 1 I into v1 is equal to 0. We all know. So 0. Either you solve this equation, this black equation, I mean the equation written in black, or you can solve this equation, the equation written in red. You will get a both, in both scenario you will get a same answer. So here in the red, the equation written in red, you have to multiply a minus lambda 1 I twice, and then you have to find out the a minus lambda 1 I square, and then multiply it with u1 and equate it with a 0, similar to this a minus similar to this equation, and then find out the u1. Similarly, for that this case, if we multiply, let's say once, you will get u2. This is a minus lambda 1 I u1. This a minus lambda 1 I u1. Okay. So what you multiply another time u2, you will get a minus lambda 1 I square u1. This is equals to 0. So either you solve this equation, you have to multiply it first twice, then thrice, then fourth times, then fifth time. Depend upon the how many eigenvalues are there. If let's say if it's a 5 cross 5 matrix, okay. So and all the five eigenvalues are okay, repeated eigenvalues. All the five eigenvalues are the repeated one. So and the geometric multiplicity is, let's say, 1. So what you should do? First you find out the v1, then you find out the u1, and from u1 you find out the u2 in that format. Or let's say you find out v1, then you find out u1 using this a minus lambda 1 I square into u1 equals to 0. Then you find u2 using the equation a minus lambda 1 I cube whole to the power 3 equals to 0. Then a minus lambda 1 I whole to the power 4 into u3 equals to 0 in that format. Whatever format you choose, you can choose it. Okay. Is it clear?
Yes.
So I'm just now moving to the next. Let me charged. Moving to the next thing, that is stability. So here the stability. So what is basically a stability is? So we need that our system should not for a given input, whatever the input I am giving, our system's response or the state response should not grow unboundedly. If it grows unboundedly, that system is not a stable system. If it does not grow unboundedly, if let's say with respect to time, the all the state values is decaying in nature, that means the system is stable. This is basically a layman definition of stability. Now, in a mathematical format, what we say, so let's say I'm considering any system. You can think of it as a linear system, non-linear system, anything. Let's say, let the system is x dot equals to f of x. Okay. This is basically an autonomous system. Autonomous system means if there is no forced input over here, just system is driven by its initial condition. So you can think of it, this function f as a linear function, non-linear function, whatever. I'm not going into detail of that. And its initial condition is x at t naught equals to consider as a x naught. So this definition of stability is also called epsilon delta approximation, epsilon delta definition. Sorry. So what it says? It says that x equals to,
Excuse me, sir. What is that
yes,
last word you told? That stability is.
ep, epsilon delta definition.
Oh, okay, okay, okay.
Okay. This epsilon delta definition. Okay. So I'm saying that x equals to 0 is a stable. This is, let's say, this is an equilibrium point of the system x, is an equilibrium point of x dot equals to fx. Okay. So the equilibrium point is said to be, first is stable. If I'm just first let me draw the diagram and then I will discuss later. So we say if for a given so the definition is, yeah, for a given epsilon greater than 0, let's say you are given that the epsilon is given to you, let's say okay, 1 meter radius. For a given epsilon greater than 0, this is the origin and this is the epsilon. Okay. So for a given epsilon greater than 0, we'll always get a delta. Pardon my drawing. These all are considered as a square, a circle or a ball. Okay. So this is a delta. The radius of is delta. That's why it's called epsilon delta definition. For a given epsilon, if there exists a delta, okay, always epsilon greater than 0 and delta greater than considered as a 0, obviously. Then if the initial condition starts from delta, the system's trajectory always lie within this epsilon. It will not, it will never cross this epsilon border. So if x naught is less than or equals to, if x naught is less than delta, then xt will always be less than epsilon for all t greater than t naught. Is it understandable? Like if we start, if any system start very near to the very near to its equilibrium point, if any system start very near to its equilibrium point and it will never exceed this epsilon boundary, then we say the system is stable. Okay. And system is unstable. System is unstable means we never get a delta for that. For a given alpha, for a given, for a given epsilon, we never get delta. And system is asymptotically stable. System is asymptotically stable when it is stable and it converges to its equilibrium point. I'm considering here 0 is the equilibrium point. So that means, let's say this is epsilon ball and this is delta ball. This is 0. Okay. So this is epsilon ball, this is delta ball. And let's say system.
Hello, sir. Hello.
Yeah. Hello. Hello.
So this topics I know. If you want, you can skip.
Okay, I can hear. Okay. So it will converge to the origin, then the system is asymptotically stable. So now comes to the next point is, so I'm not going to discuss then about the positive definiteness of the system. Okay, so I think you know how to find out the positive definiteness, the Sylvester
Yes.
criteria. So I'm not going to discuss it over here. So just give a short short preview basically, just for the others who will see the recording for later. So to find out the definiteness of a matrix, whether it's a positive definite, positive semi-definite, negative definite, or negative semi-definite. So we have to check the principal leading minors. If this term is greater than 0, this whole term is greater than 0, and this whole term. So the first A11 is greater than 0.
That is all
Then,
principal minus should be positive, isn't it?
all the leading principal minors should be greater than 0, and the final determinant is greater than 0. Then this is basically positive definite. Positive semi-definite, in case of positive semi-definite, this should be that determinant of A. In case of positive semi-definite, if a system is a positive semi-definite, that means if a system, first of all, if a system is positive definite, that means all the eigenvalues are positive. I mean, they always lie in the right half of the complex plane. For a positive semi-definite, at least one eigenvalue is 0. If one eigenvalue is 0, that means the determinant of the matrix is basically 0. Okay, so in that case, this determinant of A should be less than or equals to 0. Greater than or equals to 0 is there. So this is basically the Sylvester criterion. But here, sometimes it happens that it shows that this criteria, this only checking the leading principal for in case of positive semi-definiteness, if you see, you will see that only checking the leading principles is not the sufficient one. In that case, you have to check the other minors as well. And if you say, let's say if one of the minors is -1, another minus is +1, then you will say that that matrix is indefinite. You cannot conclude its definiteness. So why this symmetric positive definite, or why this symmetric positive definiteness is really important in stability it comes to the next picture where we'll talk about the Lyapunov. So you know the Lyapunov. So should we broadly discuss about the Lyapunov, or we just go through the examples and see what happens? Hello, hello.
Hello.
Should we? I mean, do you know the Lyapunov stability? I mean, should I need to discuss it broadly, or just go through the examples and?
I know that. No need to go through that.
Okay, so I'm just giving you a few examples, and then we will wrap it up. Okay. So Lyapunov functions is basically, we need to find out, is basically an energy based method. So what it basically says that if the system's energy is decreased by if the system energy is decreasing by time, as the time goes to infinity, if the system energy is decreasing, then we can say the system is stable. But every time to find out the energy of a system, like the potential energy and kinetic energy of a system, is not possible. If the system is too complex, then it is hardly difficult to find out the energy of a system and then check whether its derivative is decreasing, if the slope of the derivative is decreasing one or not. So it is difficult. So the Lyapunov, the scientist Lyapunov, what it says that, okay, there is no need to find out, or no need to check the no need to find out the energy of the system. If you try to find out the stability of the system, you can use any continuous differentiable positive function, and you can use it and check whether the derivative of that function is a negative definite or negative semi-definite or not. So in that case, all the time you no need to find out the energy of the system. Sometimes you just use the state of the system. Using the state of the system, you can generate a positive definite function as well. Okay. So first example is, I'm giving you an pendulum example. So this is the pendulum equations. I'm not discuss about the how these equations come from. I'm just, this is basically the pendulum equation. So here theta, m is the mass of this bob, and the L is the length, g is the gravity due to acceleration, and theta is the angular displacement. So I'm considering this x1 as a theta and x2 as a theta dot. So transfer this equation into a state space format. So what do I get? X1 dot equals to x2, and x2 dot equals to minus b ml square x2 minus g by l sine x dot. So this is basically, you can see this is the nonlinear equation because this sign term says exist over here. So due to this, it is a nonlinear equation. Now, this is basically a simple system, so we can find out, we can easily find out the energy of this pendulum. So what is the potential energy? The potential energy is, we know it should be mgh, mgh. So h is this term, this is L sine theta. Okay. And from where to where I'm going to calculate this mg sine theta from initial position 0 to theta. Theta means x1. From 0 to theta, I'm finding out what is the potential energy of the system. Okay. So if we calculate, we will get mgl 1 minus cos theta, or mgl 1 minus cos x1, because we choose x1 as a theta. Now the kinetic energy is half mv square. Linear velocity. So linear velocity is basically equals to length into angular velocity. So what do we get? Half ml square into theta dot square. Now this term is positive, right? Because this is positive term and this is positive term. Because ml can't be negative, theta dot square is there. So whether if the value of theta dot is negative, it will always give you a positive result. And cos x1 always lies within the -1 +1, within in between the -1 +1. So this term is always positive. So we choose Vx as a Lyapunov function, or should we say a candidate Lyapunov function, mgl 1 minus cos x1 plus half ml square. We consider this as a half ml square x2 square. x2 square. Now if we differentiate it, what we will get? We will get mgl sine x1 into x1 dot plus ml square x2 into x2 dot. So what we get? X2, sorry, mgl x2 sine x1 plus ml square x2 into minus b by ml square x2 minus g by l sine x1. So if we multiply, we will get b x2 square minus mgl x2 sine x1. So this term goes to 0. I have bx2 square. So could you tell me whether it's a negative definite or negative semi-definite? This v dot is negative definite or negative semi-definite? Am I audible to you? Hello. Hello. So this term is basically negative semi-definite. Yeah.
Semi-definite. Okay.
Yeah. Yeah. So this term is negative semi-definite because here x1 term is not exist. Because so if we choose, let's say x1 equals to anything -1 and x2 equals to 0, sorry, x2 equals to
That's okay, sir.
-5.
X1 is absent,
Yeah.
no? So it can be anything. So
Yeah,
we
yeah.
can say semi-definite. Okay.
So just let me, I'm just explaining this because someone will see the
Ah,
recording, that's why.
okay, okay. Oh, recorded session.
Yeah,
Okay.
yeah. So that's why I'm just saying. So in that case, because we choose any value of x1, I mean, this term is always give you either less than 0 or equals to 0, right? So it does not, the value of v dot does not depends on the x1. It only depends on x2. So we will always say that this is term is a negative semi-definite. So when it is a negative semi-definite, semi-definite means the energy is not constantly decreasing. At some point, you will see that energy is constant. It is not going, it is not increasing or it is not decreasing. It is just constant. So in that case, the system is, so by solving this Lyapunov equation, we can say the system is stable in the sense of Lyapunov. Okay, we cannot say the system is asymptotically stable. If if it happens that v dot equals to, it is if and only if situation. So if v dot equals to, let's say, bx2 square minus some x1 square, if this happens, so that means for any value of x1 x2, it is always v dot gives you always a negative result. Only if v dot only gives you a zero result if it is x1 and x2 equals to 0 and 0. So that means this is negative definite. So in that case, we can say the system is asymptotically stable. Means as the time tends to infinity, system goes to the system energy goes to the 0. So now this is, since this is only depends on x2, not on x1, so this is semi-definite and it is stable one. But here the Lyapunov concept, this is not a necessary condition, because for this function, using this function, we find out that the system is negative, the system is stable one. But there maybe exist another functions. Using that function, we cannot conclude anything about the stability of the system. So we will see in the later example. For that case, I'm just giving you another example, and I'm just asking you what should be the value. Please response. So let's say I have this kind of graph. Okay, so you have a system is something like the x0 equals to minus g of x. So for that case, and the question is the system stable? So you are not giving any kind of what is the value of g of x. You're just giving that the only graph of the g of x. So the first thing, what should I do? So I should do, consider, we can choose, as according to Lyapunov, we can choose any continuous differentiable positive definite function as a candidate Lyapunov function. So let's say choose v of x equals to 1 by x square. So this is positive definite, continuously differentiable. Okay. So we find out the v dot, we get x into x dot. So what do we get? Minus of x into g of x. Now, whether this x into g of x, is this term positive or negative? Is this term positive or negative or undefined term? Could you please answer whether this xgx term is positive, negative, or undefined term? I have given to you a graph of this gx, and what do you say about?
Negative. Is it negative?
No, I'm just don't consider this negative term. Only consider the xgx. Is xgx is positive or negative? Is this positive, negative? What should be the value, or it is undefined? You have the graph system.
Positive.
It is always positive, because as the system x is increased, you see that gx is increased, gx is positive. If x is negative, gx is negative. So this term is always a positive term, always positive, huh? So this whole term is always negative
Negative.
definite. So in that case, we can conclusively say that our system is asymptotically stable. Not only stable, the system equilibrium point is asymptotically stable. Now I'm just giving you another example. So the system is, let's say, x dot equals to, x dot equals to x2, and x1 x2 dot equals to minus x1 cube minus x2 cube. Okay. and we that whether find out the stability of the system, whether the system is stable or not. Okay. So first I'm checking, I'm considering one function, let's say half x1 square plus half x2 square. So first of all, I have to check whether this is a positive definite or not. X1 square, x2 square, whatever the value of x1 and x2, this is always positive. This is always continuously differentiable. So we can choose this function as a candidate Lyapunov function. Now I have to check whether using this candidate Lyapunov function, can I conclude the stability of the system or not. So let's say v dot of x, we will get x1 dot plus x2 dot. So what do we get? X1 x2 minus x1 cube x2 minus x2 to the power 4. So from here, we cannot conclude anything because no terms is basically eliminated. We cannot eliminate any term, any undefined term. We cannot eliminate this term. We cannot eliminate this term. This term is positive, that is for sure, but we cannot say anything about this x1 cube into x2 and x1 x2. So what does that mean? This means
Right.
right, we cannot define anything about the whether the v dot is negative definite, negative semi-definite, what is, we cannot define. So that means this is undefined, right? So that, does that mean that system is not stable one? No, we cannot say, because for this Lyapunov function, we cannot say anything about the system. But there maybe exist another Lyapunov function using which we can say about the system stability. So that's why this Lyapunov, for a nonlinear system case, this Lyapunov functions is only gives you the sufficient condition. It is not a necessary condition. Means if you find v of x by derivating this v of x, if you get a negative definite answer, then the system is stable. But if you cannot find, that does not mean you will never find. Maybe there exists, मतलब वहां तक तुम सोच नहीं पा रहे हो, maybe there exists something. So that's why it is sufficient. Now I'm using a different v of x. Let's say 1 by 4 x to the power 4 plus half x1 x2 half x2 square. So this is also a positive definite function and continuously differentiable. And now what I am doing, x cube into x1 dot plus x2 into x2 dot. So what I will get, x1 cube x2 minus x1 cube x2 minus x2 to the power 4. So I get x2 to the power 4. Now I give at least a conclusive result. I get a conclusive result that at least v dot x is negative semi-definite. Okay. So if we, so this is the Lyapunov function. This is the actual Lyapunov, I mean correct Lyapunov function to find out the stability of the this system. Now in case of a okay, let me give you another example. This is, so here I talked about x equals to 0, the stability of the equilibrium point x equals to 0. Okay. Now what happens if the system's equilibrium point does not exist in a 0 point? What happens? It's not always the case that we will get the system equilibrium point always be in the 0 point. Okay. So let's say this is a non-linear mass spring damper system. Okay. mg minus ky minus b1 y dot minus b2 y dot y dot. Okay. So I'm considering x1 equals to y and x2 equals to y dot. So what we get? We get x1 dot equals to x2 and x2 dot equals to minus g minus k by m into, sorry, into x1 minus b by m into x2 B1, yeah, minus B2 by M into X2, X2. So this is my system. Okay, state space format. Now, what is the equilibrium point of this system? So to find out the equilibrium point, what should we do? We do that f of x equals to 0. This is the thing that we do, right? So the equilibrium point of the system is x2 equals to 0 and x1 equals to minus k by m x1 minus g equals to 0. So we will get, sorry, this term is 1, this term is plus. So we will get x1 equals to mg by k. So the equilibrium point is mg by k comma 0. Now I'm finding out I'm considering a Lyapunov function. Let's say half m x1 square, sorry, x2 square plus half k x1 square. Okay, so this is my candidate Lyapunov function. This is a positive continuously differentiable function. Okay, so v dot of x is basically m x2 dot plus k x1 dot. So m x2, what is x2 dot is g g, sorry, plus k, sorry, minus k by m x1 minus b1 by m x2 minus b2 by m x2 plus k x1 dot is x2. So what we get? We get mgx2 minus bx2 square b minus b1 x2 square minus b2 x2 square x2. So from here, we definitely can't comment about the stability of the system because of this term, right? So this is basically undefined. Now we choose a state in a defined format. So in first case, what we choose? We choose x1 equals to y and x2 equals to y dot. This is our state. Now we choose a state in a defined format. Let's see what happens. So let's say x1 is considered as the y minus mg by k and x2 equals to y dot. Okay. So what we get? So x1 dot equals to, if we take a derivative of x1, we will get x1 dot equals to x2, because this term mg by k is the constant term, so the derivative of mg by k is 0, and x2 dot equals to what I get, k by m x1 minus b1 by m x2 minus b2 by m x2 mod of x2. So what if we choose v of x equals to half m x2 square plus half k x1 square? So v dot of x, you will get minus b1 x2 square minus b2 x2 square into x2. So this term, at least you can say that this is the negative semi-definite, right? So sometime you have to choose your state accordingly based on the equilibrium point of the system. So in that case, you can at least comment about the stability of the system. But if you choose in that format, choose the states in that format, in this format, you will not find out the maybe, I mean, for this, at least for this Lyapunov functions, you did not find the stability of the system. You did not find the negative definiteness of its derivative. So sometimes you have to choose the states accordingly, or you have to choose the Lyapunov functions accordingly. Now for the linear system case, this Lyapunov function gives you the necessary and the sufficient condition. The main point of the linear system is the equilibrium point of the linear system is only one. But for case of nonlinear system, the equilibrium point can, I mean, it is basically multiple equilibrium point. Let's say you can assume that pendulum, it has a multiple equilibrium point. It's not a exact one equilibrium point. So that's why for a nonlinear system case, Lyapunov stability gives you a sufficient condition, but for the linear case, it will give you a necessary and sufficient point. So in Lyapunov, just for last, I'm just saying. So for linear system case, the Lyapunov function, how we define this Lyapunov function? So the theorem basically says that, I'm just writing down the theorem and I will wrap it up. So the system is, let's say x dot equals to ax. I'm just considering about the unforced system. There is no b, there is no u term. Okay, just x dot equals to ax. So the matrix A. First of all, the solution of this equation xt equals to e to the power at into x0. So we know that if the eigenvalues of the A is negative, all the eigenvalues of A lies in the left half of the complex plane, we see that at t tends to infinity, xt tends to 0. That means the system will not blow up. This will be a stable system. So we want a Hurwitz matrix. A should be the Hurwitz matrix. So the matrix A is a stable matrix or Hurwitz matrix, whatever. If and only if for given positive definite matrix, sorry, this should be a symmetric positive definite. For a given symmetric positive definite matrix Q, there always exists a symmetric positive definite matrix P which satisfy the following equation, which is A transpose P plus PA equals to minus Q. So this equation calls Lyapunov equation. Okay. So if for a given, so first for a given Q, symmetric positive definite Q, if we, there always exists a symmetric positive definite matrix P which satisfy this equation. If this happens, then A matrix is always a stable matrix, means all the eigenvalues lies in the left half of the complex matrix. So first of all, you have to choose Q first. So the thing is, you have to choose Q first and then solve for P. You can't do this reverse way. I mean, let's say if you let's say you choose the P first, and then if let's say you choose the P as a symmetric positive definite matrix and then solve this equation, try to find out the value of Q. You will never get a symmetric positive definite matrix for Q. You will never, sometime you will get, sometime you will not get. So that's why you have to choose Q first. You have to choose Q as a positive definite matrix. So the trivial choice of Q is basically identity matrix I. Okay, so you can you first choose Q, then you solve for P, and then you will check that the P is always be a positive definite symmetric positive definite matrix. Then the A is Hurwitz one. So this is for the linear case. For linear case, you have to solve this. What you should choose? You should V of x should be considered as a x transpose Px, where P is the symmetric positive definite matrix. Okay. Now, if you consider this x transpose, this x dot transpose Px plus x transpose Px dot, what you get? A transpose Px plus x transpose Pax. So this is basically the actual things comes from. So if this term is negative definite, then if A transpose P plus PA is negative definite, then V dot X is negative definite. So that's why you consider as the A transpose P plus PA is equals to minus Q, where Q is a positive definite and minus Q is a negative definite. Okay. So I hope everything is have, I am able to clear the doubts or whatever, or if there any kind of doubt, so you can ask me. If not, then I can wrap this discussion. Miss Vishalakshi, is there any kind of doubt that you can ask me over here?
No doubt.
So is it clear, right?
Yeah.
Yeah. So I'm just then wrap this thing. I mean, wrap this discussion. Okay. So I'm just stopping this recording. Okay.
Okay. Can I ask one not
Yeah.
related
Yeah.
to
Yeah.
this?
Yeah.
Not related to. Actually, I forgot to do the registration, so it is not possible to register now. No, today, yesterday was the last date.
Registration for exam.
Exam, yeah.
Okay. So I mean, did you? I mean, mail the NPTEL team because I'm not able to. I mean, open the portal right now because I do not have this access. So,
Okay. Okay.
if it is, I mean, possible to mail the NPTEL team, then you can ask them just to increase the date, let's say 1 or 2 days, for 1 or 2 days, because I'm not allowed. I do not have any access for that.
Okay. Okay.
Okay, okay. Okay, then. Thank you, and see you in
Thank you.
next, yeah, next class.